Okay, now first of all, we know that when we form a covalent bond is formed from a sharing of electrons. In other words, both orbitals must contribute one electron. Okay, so you can see there's one electron from each of the orbitals. According to valence bond theory, this head-on overlap could occur between s and s orbitals. Okay, let me just play the video. Okay, it can occur between s and s orbitals head-on overlap, which will give you a sigma bond, or between s and p orbitals, or even between p and p orbitals. Okay, and this is your sigma bond. Both orbitals must have an unpaired electron, and they must combine and share these electrons to form this sigma bond. Okay, so first of all, let's look at some of the issues associated with this valence bond model. Okay, I'm just going to look at a methane molecule, CH4. Okay, this is a CH4 molecule as an example. Now, in case you are lost at any point in time, okay, you can look at my top left-hand corner. This will tell you which page I'm on in your lecture notes. So currently, I'm on page 2. We're looking at hybridization. Okay, but even before we look at hybridization, let's look at some of the issues with the valence bond model. So that's why you will understand why we need a newer model. Okay, so if we look at this, to form a CH4 molecule, my carbon needs to form 4 bonds. Okay, and we know that our carbon atom has this electronic configuration. Okay, 1s2, 2s2, 2p2. Okay, previously we have also examined what it means to be a covalent bond. You saw that the orbitals need to have unpaired electrons in order to form a covalent bond. So if you look at this electronic configuration over here, how many unpaired electrons are there? Okay, you're going to see that a carbon only has 2 unpaired electrons. What does this mean? Potentially, it can only form 2 bonds. Okay, so in that case, how is it able to form CH4? Okay, when that requires 4 bonds. Okay, so in order to form 4 bonds, I need to excite my electrons. Okay, look at this. I'm going to excite one of these electrons in the 2s orbital up to my 2p orbitals. You know that 2s is lower in energy than the 2p. Okay, so I need to excite it. Once I excite it, what do you realize? I have 4 unpaired electrons. This is the excited state carbon. Okay, I now have 4 unpaired electrons, which means potentially this allows me to form 4 bonds. Okay, but there's still a problem. Okay, what is the problem here? Okay, we know that. Okay, let's look at this. Where are my unpaired electrons? They are in my s and p orbitals, and we know that p orbitals are aligned according to the x, y, and z axis. What does this mean? Okay, let's say this is my carbon. Let's say I have one p orbital here. I have another p orbital that is 90 degrees to it. Okay, you know that the p orbitals are all aligned along the axis. Axes are all 90 degrees away from each other. Okay, and let's say this is my third orbital, which is 90 degrees as well. And in each of these orbitals, there is 1 unpaired electron. Okay, so you saw earlier in the valence bond theory, okay, in order to form the sigma bonds, is going to collide head-on, overlap head-on. So my hydrogen is going to come in and overlap. Okay, yes, the unpaired electron is going to overlap head-on with the unpaired electrons here. Okay, but what is the problem? You realize that it means that my methane molecule will have a bond angle of 90 degrees because of the way the p orbitals are oriented. But we know that is not true. Okay, a methane molecule we know has a tetrahedral conformation. Okay, it's a tetrahedral geometry. The angle should be 109.5 degrees, not 90 degrees. Okay, so therefore there's a problem over here. Okay, so how are we going to overcome this problem posed by the valence bond theory model? Okay, because now we have seen that the bond angles are not correct. Okay, so that's why we have to introduce a new model called the hybridization theory now. Okay, so what is hybridization? Hybridization, in other words, actually just means mixing to form a new hybrid. Okay, so what we're going to do now is to form new orbitals. Okay, so we take our excited carbon. Okay, we need the excited carbon so that it has 4 unpaired electrons. Okay, and we know that Okay, this is how the orbitals look like. We're going to take 4 of these orbitals, we're going to throw it in, and we're going to mix it together. Okay, and because I took an s orbital and 3 p orbitals, that's why it's going to be called sp3 hybridization. Okay, I'm going to mix them up, I'm going to form new orbitals. Okay, these are called sp3 hybrid orbitals. Okay, these are new type of orbitals. So because I took 1 s and 3 p, total 4 orbitals, I should end up with 4 orbitals as well. Okay, and this is how they look like. Okay, these are the 4 sp3 hybrid orbitals, and we can combine them together to give me my tetrahedral geometry. Okay, in your notes on page 3, you will also see the word degenerate. Okay, degenerate means they have the same energy. Okay, so previously my s orbitals, this is my 2s, this is my 2p. My s and p orbitals, you should know they have different energy levels, but now they end up with these 4 sp3 hybrid orbitals. They are all of the same energy. They are all degenerate, so they are all equivalent to each other. Okay, and that's why I end up with a tetrahedral geometry. Okay, 109.5 degrees away from each other. Now I want you to look at this orbital, okay, or any of them, because they are all the same. Okay, they are all degenerate, they are all the same. If you look at this sp3 hybrid orbitals, you look at the shape, is very interesting. Okay, there is a big loop and a small loop. Okay, why it looks like this is because this is a cross between the s and the p orbital. S orbital looks like this, a p orbital looks like a dumbbell. Okay, and if we mix them together, we get something called a hybrid orbital. The hybrid orbital is going to look somewhere in between a s and a p orbital. Okay, this is another way of looking at it. Okay, as I showed you earlier on. Okay, previously, you know, the s and p orbitals, they are of different energy levels. After I hybridize them, these 4 sp3 hybrid orbitals, they are all of the same energy. They are all degenerate. Okay, this is in your notes. Okay, and you can see that. Okay, this is how the s orbital looks like. This is how the p orbital looks like. After I mix them together, I'm going to get a new orbital called hybrid orbitals. This looks like a cross of a s and p orbital, somewhere in between. Okay, so this is how sp3 hybridization occurs. Okay, so once I have my sp3 hybrid orbitals, this is my carbon. My carbon has 4 sp3 hybrid orbitals. My hydrogen can come in to form my methane molecule 109.5 degrees away. Okay, so no issues here. Okay, I'm going to show you a quick video on how this looks like. Okay, so as you can see here, I have my s and p orbitals, 2s2, 2p2, which is my ground state carbon. Okay, later on you are going to see it gets excited, and then after I hybridize, they all become degenerate, okay, of the same energy level, and I have 4 unpaired electrons here. Okay, let me just skip forward a little bit. Okay, these are all my sp3 hybrid orbitals. Okay, so as you can see here, this 3 here represents, because I use 3 of the p orbitals in this hybridization. Okay, so that's why it's called sp3. Okay, so in total I have 4 sp3 hybrid orbitals. Because in total I use 4 orbitals as well. I use 1 2s and I use 3 2p orbitals. Okay, so let's just take a look at how they look like. Okay, so if you can see this. Okay, initially your electrons, your unpaired electrons are in your p orbital. Okay, which is 90 degrees. Okay, this will not give me the bond angle that I want. But after I've hybridized, okay, I come up with 4 equivalent sp3 hybrid orbitals. I get 4 sp3 hybrid orbitals. You can see that they are now equivalent and they are now 109.5 degrees away from each other. Okay, and once I form my, okay, let me rewind a bit. Okay, so you can see the 4 sp3 hybrid orbitals, they are 109.5 degrees away from each other. Okay, which is the bond angle that I want for my methane molecule. It's tetrahedral. So once I have my hybridized my carbon, okay, my hydrogen can come in. Okay, my hydrogen can come in to form the 4 sigma bonds. Okay, let me show you that part again. Okay, my hydrogen is going to come in to form the 4 sigma bonds, the head-on overlap. Okay, but take note now, the head-on overlap is between the s orbital of hydrogen and the sp3 hybrid orbital of carbon. Okay,